Algebra 2, welcome to 10.2. This is all about circles. So you have in your packet like 6 or so page thing of notes, so 10.2 notes on circles. Not because this is hard, but because someday I missed school years ago, some year, and I had prepared this lesson to be given in my absence for students to just read this packet without me existing in their life for a day. So you have a double bonus here of packet that you could probably do completely without me, plus a video to support that. So you should be in much better shape than whatever year that they simply got the packet before I was TMR the Mad Wizard. What this is about is circles. So the first thing to just tell you is the definition for a circle. It's a set of all points in a plane. Plane means a flat surface, like my board. Equidistant means the same distance from the center. So what that means is, if I drew myself on the board a center first, this point is some distance away. So is that. So is that. So is that. And this, and this, and this, and this, and this, and this. And if I had the patience to sit here, every one of these points that I'm drawing is the same distance as all of the others from my finger, if I could draw. And if I did this all day long, sooner or later, I'd end up with a circle. Okay? Every point on this circle is the same distance from the center as every other point. That distance, if we measured it, would be called the radius of the circle. You might remember circumference going around, diameter went the whole way through. Radius is our key word of this chapter. The point right here is called the center, and you could just sort of read that page for yourself if you wish, but that's the basic gist of circle concept. If you want to graph a circle, and in the homework you're going to need some graph paper. If you're quarantined in your home and you have no graph paper, I guess just do what I do on my board, which is I kind of self-make my own. But I'd rather use graph paper if you own it, or if you make your way out to a Walmart or something trying to pick some up. That would be of more advantage to you. Your pictures will just look better. But if you're going to graph a circle, you'll first graph the center, and then from there go 4 points that surround it, north, south, east, and west. So the picture that I'm doing here on page 2 is I want a circle that has a center at 2, 3 and a radius of 4. So the first thing to do is go over 2 and up 3. There's the center. That's the point, 2, 3. You don't have to label it 2, 3. I just did because I felt like it. If the radius is 4, I need to go in no particular order up 4 blocks directly above the center, down 4 blocks directly below the center, to the right 4 blocks on the same height as the center, and to the left 4 blocks directly to the left of the center, sort of like north, south, east, west, all 4 directions, go that 4. And then do your best to make a circle, not a diamond. If you draw straight lines, you're going to have a diamond, and that's not what we're after. But what we're trying to do is like round this off. And if I had graph paper, that would be a little bit better circle looking. Everybody's circle is going to probably be a little bit ovalish. That just is how it is. Equations of circles. So as long as the center is at the origin, you're going to get always the same beginning to every equation if the center's at the origin. X squared plus y squared equals. That's how every equation will start if the center's at the origin. Then there's a number that depends on the radius. The number will always be the radius squared, times itself, in other words. So if I want the center at the origin and a radius of 3, I'll go x squared plus y squared equals, and I do a 9, because 3 squared is 9. If I want the center to stay at the origin, I'm going to do that same beginning. But if the radius is 7 now, I need to go 7 times 7, and that would equal 49. If I'm still at the origin, I'm still starting this way. But if this is my radius, this times itself, remember, roots times roots make the regular version of themselves. That would just become a standard 11, not a root 11 anymore. We're about halfway through the page. Those are the ones that I did on the top half. On the bottom, we're just working in rewind mode. So if I tell you the equation, because those all have the same standard beginning, they are all centered at the origin. Anything at the origin has x squared plus y squared equals. Anything with x squared plus y squared equals is centered at the origin. If I throw a 25 in the problem, you give me a 5. When we traveled in this direction, we were squaring. Now that we're traveling in that direction, we're rooting because we're doing the opposite. So this radius would be a root 10. This wouldn't be bad as root 20, but again, anytime we start doing roots, we're thinking about those squares and this list that I draw up, it seems almost every day of my life. 4 helps us by going into 20 5 times, so 2 root 5 is my best answer there for radius. However, you cannot always count on every center to be located at the origin for your entire existence. If the center goes somewhere else, we would get an equation that looks like this. If you start seeing some parentheses and some adding and subtracting, just like chapter 9's beginning, where we did a lot of right, left, up, down movements and stretch and tall and flips and all that, as soon as you see the adding or subtractings, you're going to move some things around. So if it's x minus 2, that puts an x to be 2, opposite sign. If we go y minus 3, the y would be a 3 for the center. But the radius just keeps playing with you the same way. The 16 becomes a 4, because traveling in this direction to get a radius, we would root. If I wanted this to be a negative 2, I'd go x plus 2 squared. If I wanted this to be a negative 3, I'd have to go y plus 3 squared. There's still an x, there's still a y, there's still squares, but the adding or subtracting is what's changing the center. And then if I say radius is 6, this should equal 36. Because when I work in that direction, I'm trying to square. Coming back the other way, this center would be a negative 5 because of a sign switch from the x. It'd be a positive 6 because of a sign switch of the y. The radius would be an 8 because the root of 64 is 8. This would have a center of an x with 1, a y with negative 3, and the radius would be root 10. At the very end of the homework, they're going to throw you some that look like this and ask you to do the same thing, and that you probably quickly realize just does not look right. That is not the way you want that to look. So we're going to have to go back to our factoring skills. And this is a thing, again, called factoring by completing the square. We're trying to make squares. This whole lesson relies on things being squared. Everything's been squared the whole day. So on a problem like this, we're going to have to do some completing the squares. I'm going to sort the x's together. X squared and 8x are together. Y squared and the 2y are together. And I'm going to kick the 15 out of there, and it switches signs when I kick it out of there. Opposites and all that, subtracting, it's negative 15. To make squares, we're going to get a pair of them. X is going to run the one problem. Y is going to run the other problem. I'm going to end up creating some numbers as always. I'm going to have to pay for those as always. Rule on completing the square is, was, and always will be, keep the sign, go half of the number. This times itself is always positive. 16, that's my created number. If I'm going to add 16 here, I'm going to add 16 there to pay for it. For my y's, minus to keep, 1 to cut in half, plus always. This times itself is a 1. to pay for adding 1, I'm going to add another 1. Tally that all up, and that'll tally up to 2. And now we're good. So our center would be a -4, +1 from changing these signs. The radius, we would try to do the square root of 2, and that's just the square root of 2. Quick peek at potential homework problems. Here's something that might make some people mad. If this were a 1/16, all that this would do to us is have a 1/4. Just like if this had a 25/36, this would have 5/6. Just do each top and bottom as their own little root. Don't let that bother you. Here's another maybe thing that would make people mad. If this were 3√5 and we try to square our way back, this 3 would still become a 9. That √5 would become a normal 5. 9 times 5 would be a 45. So again, for example, if this had not just a 7, but like a √2, the 7 would become 49. But the √2 would become a normal 2, and you'd have to multiply them to make a 98. 427, other things. I see there's a problem that has a pi. Don't let that bother you. If this is a pi, and we're stepping in this direction, it's just pi squared. That's okay. Don't let that make you mad. I think we should be good other than that. Every problem, they want you to do the center or the radius, center and the radius, excuse me. And then I believe my instructions on the syllabus are to graph the even ones only. That's true. So anything even, we'd want to graph it. If you did try to graph something like √11, just use your calculator, punch in √11, it's like 3 point something. It's probably like 3.3. Yeah, let me see. Handy, here we go. So if we do the root of 11, it is 3.3, right on the money. So if I were going to try to graph this one, center's at the origin. If I'm trying to graph 3.3, I'd go 3 squares and a little more, 3 squares and a little more. Every direction I'd go 3 squares and then a little more, and I would circle that up. So in the midst of doing all this center radius stuff, we're going to graph the even ones. Always do the center first, and then the radius takes you all 4 directions to try to make a circle. On the last page of notes, I did explain that if you were trying to graph something like √30, use your calculator to see it's about like 5.5, and then you just kind of guesstimate where 5.5 would look like. So, homework 427, that's it.